My name is Chris Barkin, and I want to welcome you to the William W. Hay Railroad Engineering Seminar. But before I introduce our speaker, we have some housekeeping items as usual. If you have a cell phone, please take it out and turn it off or put it on vibrate or whatever. If we have a fire alarm, just exit from either of these doors that have the exit sign marked and proceed to the nearest exit outside the building. And then we'll gather on the south side or the north side of Main Street. And I'd ask you to look to your left and right and front and back, and we'll use the buddy system to make sure that everybody gets out safely. We're not expecting any severe weather, but if we did, we would, instead of going outside, we would exit down back into the old part of Newmark Lab and then descend the stairs to a safe refuge down there. Do we have the attendance sheet going around? Okay. So if anybody did not swipe,
This is the sign.
yep. So anyway, those of you who haven't swiped or signed in, please sign the attendance list. And are we going to be using the microphone for? Yeah. Yes. Okay. And so I also want to ask the speaker, if we get questions from the audience, we'll try to get a microphone to them. But if we don't, if you could just repeat the question for the benefit. We have a pretty good number of people who have tuned in online. Darkin, do you want to give us just a brief announcement about happy hour? Just tell us where and when.
Railtech has a 30-minute happy hour at the Wine Co., which is 120 North Walnut Street. Everybody's invited, and the weather seems to be pretty cold, but still, we thought that we should move it inside. So today it will be at Wine Co.
So we're live now, right? Okay. The William W. Hay Railroad Seminar Series is sponsored by the National University Rail Center here at the University of Illinois at Urbana-Champaign. And on behalf of all of us, I want to thank the US DOT for their support. It's greatly appreciated by those of us here on campus, as well as those participating via the internet. Let me briefly welcome those of you who are joining via the internet. This includes representatives from Union Pacific Railroad, CSX, Metro North, Hanson Professional Services, Boise State University, Federal Railroad Administration, Train Dynamics, the WEGH Group, Illinois Department of Transportation, Jacobs Engineering, Sharman Associates, North Carolina Department of Transportation, Patrick Engineering, Quandl Consultants, Chicago Transit Authority, and ESI. We are very glad you could join us this afternoon. And if any of you would like to receive PDHs for your participation, please send LB an email with the information as described in the email announcement for this seminar. So today's lecture is going to address what I think is one of the most interesting engineering challenges facing railroading today. How do we combine heavy axle load freight trains with higher speed passenger trains using the same infrastructure? We need to consider load environment, modes of failure, factors that drive engineering design and maintenance considerations, as well as discussion of several selected track engineering problems to include rail fatigue and track buckling. It's almost impossible to think of a more qualified speaker to address this topic today. This is Dr. Allan Zarembski. He's an internationally recognized authority in railroad track and vehicle track systems analysis, railway component failure analysis, track strength, and maintenance planning. He's currently professor of practice and director of the Railroad Engineering and Safety Program at the University of Delaware. Prior to that, he was vice president and general manager of Zetatech, an independent business unit of Harsco Rail. And before its acquisition by Harsco, Zetatech was an independent railway technology consulting firm founded by Dr. Zarembski in 1984. During the course of his career, he served as director of R&D for both Pandrel and Spino Rail Services. He's also served as manager of track research for the Association of American Railroads. And he completed his PhD and MA in civil engineering from Princeton University, and an MS in engineering mechanics, and a BS in aeronautics and astronautics from New York University. He's a registered professional engineer in 5 states. He's also an honorary member of ARIMA, a life member of the ASCE, and a fellow of ASME. He was the recipient of the ASME's Rail Transportation Award in 1992 and the AFRA's Special Act Award in 2001. Dr. Zarembski has authored or co-authored over 180 technical papers and over 120 technical articles and 2 books. Please join me in welcoming Dr. Zarembski, who will present the William W. Hay Railroad Engineering Seminar entitled Fundamentals and Selected Technical Issues for High-Speed and Heavy Axle Railroad Engineering.
Thank you, Chris. Can everybody hear me? Is the microphone working? Good. Okay, so we can get rid of my pretty picture and we can get into some technical stuff here. Okay, as Chris mentioned, the topic is fundamentals and selected technical issues, high-speed and heavy axle load railroad engineering. Okay, so fundamentals. I should say that I also give a full semester course in fundamentals of railroad engineering, so obviously I'm not going to quite get that complex. So it's going to probably be some real interesting fundamentals and some very interesting selected technical issues, more to get you thinking about the types of problems we're dealing with. Normally, in the railroad world, it's high-speed or heavy axle load. Every once in a while, they converge. Northeast Corridor Amtrak is a great example where we do run high-speed and heavy axle loads, and you'll see that the issues overlap. And some of my examples will deal with that as well. Okay, so the railroad industry. The railroad industry was wonderful in the 19th century. It started in the 19th century. So what are we doing here now in the heart of the 21st century talking about railroad engineering? Well, the good news is that it's alive and well, growing, expanding, and there are jobs for students, and there are things for professors to do, to both teach and to consult. So the railroad industry is around, and it's been the subject of technological innovation and engineering updates and incremental benefits for almost 200 years. And that's really an important point to make. You walk out to a railroad track today, and on the surface of it, it looks like the same track that we had 100 years ago. I mean, the T-rail was introduced in the 1860s. Ballast, ties. Okay, so the ties maybe are sometimes concrete, sometimes steel, but you know what? 90% of all the cross ties in the United States are still wood. So it's the same basic material we ran in the 19th century. So why is it different? Well, if you look at the steel, it's not the steel of the 19th century. If you look at the ballast and the way it's designed and the way it's maintained and the way we measure it and the way we evaluate it, it's not the 19th century. But rather than throwing out what was actually a pretty good and basic engineering design, we've improved on it incrementally. And we continue to improve on it. And that's driven by these kinds of issues, the heavy axle load and the high-speed rail issues that we're dealing with. Early railroad engineering focused on building railroads, and we're still doing some of that. Right now the big new railroad is California. California is building a high-speed railway, and we build some railways here and now, and there's some new innovative construction techniques. So certainly in China right now, where they've just built 10,000 kilometers of high-speed rail in the last, basically, decade and a half or so, there are new innovative construction techniques. But for most of the world, railroad also consists of maintaining the structure. And a lot of the innovation, a lot of the opportunities, a lot of the applications of sophisticated technology are coming to bear in the maintenance. So we sort of have two hats when we're dealing with the railroads. We have we're dealing with railroad engineering. We have the building the railroad, the designing the railroad track, and then we have the maintaining the railroad track. And railroad engineers do a little bit of both, And depending on where you are, you'll emphasize one on the other. Okay, so what constitutes a railroad? Well, railroad comes in various shapes and sizes and flavors. We have freight, which is what you see heavily in the United States. You know, the first question I'm usually asked when somebody introduces me as a railroad professor is, why do we have such a lousy railroad system in the United States? Well, the reality of it is, according to the World Bank, not according to me, according to the World Bank, we actually have the most effective and efficient freight railroad system in the world. Our passenger systems can use some improvement, but we actually have, and again, it's the World Bank talking, have one of the most effective freight systems in the world. And so when we talk about freight, we talk about conventional freight, mixed freight, heavy axle load, unit train operations. Here in Chicago, you don't have to go very far to see a bunch of freight trains going by. You just got to sort of drive down the road and see them going out. Then we have passenger. Okay, well, the high end of the passenger railroad is, of course, the glamorous high-speed rail. And high-speed rail, as we'll talk about in a few minutes, means many different things to different people. There's no uniform definition of high-speed rail. Then we have conventional interurban rail. What's interurban rail? Interurban rail is when we go from one city to another. Basically, if you take an Amtrak from Chicago to New York, that's an interurban rail operation. Oops. Let me get back. Then we have commuter rail, suburban rail. Okay, so we're in the Midwest, so let's talk about Metro out of Chicago. Metro out of Chicago is the big commuter rail operation, suburban rail operation coming here. Back in the East Coast, you have, going into New York City, you have three of the biggest commuter railroad operations in the United States, all going into New York City. Long Island Railroad, which is the biggest by ridership, Metro North and New Jersey Transit, all examples of commuter rail. And then we have transit. Heavy rail transit, which are subways and elevators. Again, Chicago is a heavy rail world. And light rail transit, which has taken on a life of its own and is growing and actually becoming really, really important in the world. I was in a faculty meeting at my university recently where they started talking about sustainability and the new interests in sustainability engineering, and the topic of sustainability cities came up, sustainable cities came up, and what followed right after was light rail transit. And in fact, you know, here we are. Light rail transit, some people will say, is nothing more than the resurrection of the old trolley. But in fact, you don't build a modern city right now without a good rail transit system. And if you can't dig underground or you don't have the money for it, light rail is the way to go. Okay, so I want to talk a little bit about the track, the engineering behind the track, maybe a little bit about vehicle-track interaction, because you really can't talk about the track without defining the load environment of the track. And the load environment of the track is primarily, but not exclusively, the trains. And so the purpose of the track structure is to support the trains at speed, guide them, because as we know, there's no differential steering in a railroad axle, so the track has a guidance function. Damp noise and vibration, which again becomes very much important. I remember one time I was in London Underground doing a grinding project. We were in the middle of the city somewhere, and the London Underground engineer came to me and said, "We can't have any noise and vibration at this location." And I asked why. He said, "Madonna lives up there." Control of noise and vibration is another of many functions of the railroad track, and one that's taken on increasing importance. And again, is one of the areas where we're looking to improve and innovate and develop techniques to do so. Okay, so the railroad track. Railroad track still is primarily ballasted cross ties, rails on cross ties on ballast. The cross ties can be wood. 90% of the ties in the U.S. currently are wood. They can be in concrete, We get about 9% in the U.S. concrete. Europe, if I go to Europe, it's about 60 to 70% concrete. They still have about 30%, 30 to 40% wood, even in Europe. Other parts of the world, often driven by the relative cost. This is where engineering economics come in as well. Those are the big two cross-tie components. But we have steel, which is a niche component, and we have growing interest in plastic and composite, which is no surprise considering the trend in society and engineering towards sustainability and recycling and more use of existing materials, non-traditional materials. So that's a growing sector. There's still some playing around with other designs other than cross ties, such as frames or longitudinal ties. But again, you don't really see a whole lot of them. If you're going to go to a ballasted track structure, it's going to be a cross tie structure. Non-ballasted track, which is either slab track or embedded track, which is your trolley track that runs in the street. That's still a very relatively small niche, even though some of the high-speed operations have started to look at it whenever you look at tunnels. Certainly if you're going underground in a metro, if you're going to elevated, now most new design elevated structures are built with direct fixation on slab track. That doesn't count New York City, which New York City, still the elevated structures are still the old wood ties without any ballast. But new stuff is usually built on slab. And so we're starting to see a lot of focus. Certainly there's a lot of engineering in here. There's a lot of interesting engineering going on. The Chinese are, again, doing a lot of work in here. The Japanese have done a lot of work in here. But if you look at the bread and butter type of track and the stuff that we're really focusing on for most applications, we're still in the good old-fashioned 19th century ballasted track with better components and better fasteners and better materials, all of which we need to deal with. So, case of you, those of you who haven't seen a railroad track, if you happen to just walk out the door and go a couple of 100 feet in either direction, and you're in Illinois, you're in the center of railroading. So this is a sort of a typical concrete tie, curve, ballasted track, fairly conventional construction, what we would consider a good, high-strength line that would be clearly, oops, I got to be careful with this changer, it's delicate. Clearly a freight line, because a high-speed railroad will never make that curve. Because if you're building a high-speed rail line, curve is the enemy of high-speed passenger, and grade is the enemy of freight. So high-speed passengers have so much power, they can go up 6, 7%, 8%. I've seen metros go up 10% plus grades. Try taking take a 14,000-ton train up at 10% grade. Good luck. It never happened. On the other hand, this is probably what? This is probably a 6, 7 degree curve. If I had to run a high-speed rail around that one, I'll probably be chugging along at 50 miles an hour, because otherwise I'll be off on the side of the road. Amtrak just demonstrated that, unfortunately, recently in Philadelphia. What happens when you try to do 100 miles an hour around a 50-mile-an-hour curve? Not a good example. Same thing happened in Spain also about 2 years ago. So it's not just an American problem, it's an international problem. Okay, and then this is a direct fixation slab track. And one of the things that happens, and one of the interesting things happens in the engineering world, is although we're dealing with sort of a rail fastener tie system here, and we're dealing with a rail fastener slab track system here, there's a lot of movement of functionality back and forth from the ties and the fasteners. For example, when we had the good old wood ties, well, first of all, wood ties were wonderful electrical insulators. I don't have to electrically isolate my rail. I can just spike my rail down, and I can run signals through it all day. I put concrete ties in there. Well, my concrete ties have steel reinforcing strands, and all of a sudden now I have to put some electrical isolation. If I put slab in there, I have to have much more sophisticated electrical isolation. Same with noise and vibration. The wood tie is basically a 9-inch thick pad. I mean, basically the pad is resilient. When I go to concrete tie, I have to introduce maybe a 6, 8, 10-millimeter pads in the structure to replace that resiliency. If I go to a slab, which is 3 or 4 times as stiff as my concrete ties, my 6/8 12-millimeter pad is now going to 20 millimeters plus. And some designs have 2 pads, just because I need the extra resiliency. Likewise, noise and vibration, the Madonna situation. Okay, now that was in London Underground, and that was slab. So guess where the noise and vibration attenuation has to come from? It's certainly not coming from the slab, so it's coming from the fastening system. The good old ballast, that piece of rock that sits out there, down there, wonderful noise and vibration attenuation characteristics. We get rid of that, and we got to replace it somewhere. Again, so there's a lot of, like I said, subtlety in the engineering, but there's some real engineering. And by the way, the design of noise and vibration direct fixation fasteners, which are important, very important for metros, is another area of innovation that continues to grow and expand. Okay, so let's take a step back and talk about the basics of design. So when you start with the basics of design, you start with your load environment, right? So the purpose of the track structure is basically to take this load, this very heavy load, as we'll show in a few moments, this very heavy dynamic load, which we'll show in a few minutes, and gradually distribute it so that piece of clay that's sitting down here underneath the ballast layer doesn't collapse and disintegrate and fail or liquefy or do all sorts of nasty stuff, but the stress levels get distributed down to the point where that it can be handled by the subgrade. Okay. This is what I call my inverse pyramid of stress, okay? At the wheel-rail interface, my stresses can be of the order of 100,000 psi, of the order of about 30 megapascals. We can go, it's an interesting situation. The whole world is metric except the United States railway system. The United States railway system is English. So when I talk to railroaders, and I understand we have a whole bunch of them listening in, I better stick to English, because when I start talking about megapascals, their eyes blur over. When I go over to Europe, the exact opposite. What's PSI? I have to go through a whole big discussion. So most of my slides will have both, so you can sort of pick the numbers you want to look at and be comfortable in. Okay, so at the wheel-rail interface, we're talking about 100,000 psi. We're actually at the yield stress of the steel. By the way, this is not your A36 structural steel that this building is built with. This is probably for standard rail, you're probably looking at something between a yield stress of probably something of the order of about 75 to 90 KSI. And if you're dealing with a high-strength stress, a premium rail, such as most railroads put in their curves, you're dealing with yield stresses of the order of 100 to 120 KSI. So you're dealing with a really high-quality steel. And again, that was part of the evolutionary process. I promise you, the steel used in the 19th century did not have a yield stress of 120 KSI. We also have a nice bending stress environment in there of the order of about 25 PSI. And then what we have to do is then we have to use this rail, which is a beam, and we'll talk about how this acts as a beam and elastic foundation in a few moments. But this rail takes this load and distributes it to a bunch of ties. Why? Because the tie bearing stress is only the order of about 200 PSI. So right away, I'm stepping my stresses down from 100,000 to 25,000 to 200. That's a whole bunch of steps. So spreading the load out anywhere between 5 and 9 ties. I put tie plates in there to spread the area on wood. Concrete can take a little bit more than 200 PSI, but not a whole lot more. It's certainly not going to take 20,000 PSI. So again, that's part of the role. Okay, then we have to go a little further. I'm not even close to what this can take. This is sort of, the AREMA standards say this can be about 20-25 PSI strength, but I will tell you a wet clay with a lot of water in there can't even handle that. Probably is going to be of the order of 10 PSI or even less. Okay, so then I have to go through my ballast. Now my ballast, if I have a really good granite ballast, which a lot of railroads will want to use, that's good for about 85 PSI. If I have a not so great ballast, then maybe I'm in the 50, 60 PSI. But you get the idea. So, and then ultimately here's my subgrade. This is what was there when I built the railroad or what I filled it in with if it was a fill. Cut, it was the original one. Fill, it's what I dumped in there to fill up the valley there. And so this is 20 psi. So you notice where I'm going. I'm going from 100,000 psi to 20,000 to 20 psi. That's non-trivial. And so, wait a minute, maybe there really is some engineering involved in railroading. And if nothing else, look over here. Okay. So, the focus of engineering analysis, you know, this is a university, so we're heavy into mathematics and we're heavy into equations, and so I'll throw a few on in there just to keep you honest. But basically, the focus of engineering analysis is the strength of the track and its components. The ability to resist catastrophic failure. Certainly, if a rail broke every time a train went over it, we'd have a big problem. So we need to do something. And by the way, that's not so laughable an idea for catastrophic failure. In the 1970s, when Amtrak first put in their concrete ties in the Northeast Corridor, they had a rash of cracked concrete ties. Why? Because it turned out the freight cars that were operating them had a whole bunch of wheel flats that were generating dynamic loads that were 3 and 4 and 5 times static loads. So all of a sudden you were seeing dynamic loads well over 100,000 pounds per wheel. And that was just cracking the concrete ties, and that led to a whole bunch of engineering and standards and controls, all of which falls into, you know, both on controlling the load and developing the components to resist the failure, such as improved attenuation characteristics of our fastening system, which now has another function, attenuating dynamic loads going down into the tie, so the ties don't crack. Okay. In addition to catastrophic failure, which fortunately we do a good job of controlling, we have the relative of that, which is long-term degradation or deterioration. And this is where most railroads tend to concentrate their focus on. And this is where a lot of research in improving materials and processes and methods and inspection techniques and analytical techniques are all focusing on. The ability to resist that long-term degradation, deterioration, maintain geometric integrity, maintain component integrity, rails wear, rails develop fatigue, concrete ties wear. We have a nice issue called rail seat abrasion, and as well as loss of line and surface, which is certainly the big bugaboo for a high-speed rail. And to control this over extended periods of time, you know, I remember when they put the last generation of composite ties in track. This was about 15, 20 years ago. Not the current generation, the previous generation. You know, they tested it in the lab and it worked well. And they put test sections out in the railroad, and after about 5, 6, 7 years, they worked fine. So they started putting more extensive numbers in. Well, ties need to last somewhere between 35 and 50 years. The average life of a wood tie in the United States is 35 years. Just average life everywhere. Not, you know, clearly Florida's not going to last as long as Nevada, but the average is about 35 years. Okay, so ties are a long-lasting item. Well, these composite ties, after about 10 or 15 years, started to delaminate. They basically lost a whole layer of the top of the tie, which is not very good, since that top layer is what holds the rail in place and your fasteners. But it took 10 to 15 years for that to manifest itself. So railroads tend to look at things with a very larger horizon. Things that work well for 3 or 4 years doesn't necessarily mean a whole lot. You know, in some cases, you know, if you're a 10-degree curve with 50 million gross tons a year, maybe the rail only will have to be replaced every 3 years. If you're a 2 MGT main line, that rail is going to last 50 years. Your horizon is very different. So we need to extend the life of track components, reduce the rate of degradation, identify, rectify problems before catastrophic failure. And one of the really hot areas that we deal with right now is improved inspection technology to allow us to identify and rectify and problems. And not only that, predict. As opposed to wait till things fail or start to fail, actually predict it. Again, that's another area of exciting research that goes out on the railroads. I get excited very easily. I get excited by railroad research. Okay, so back to the load environment, because we can't do anything on a track without a load environment. Railroads are subject to vertical loads coming down from the vehicle, lateral loads, primarily going around curves, but if you have truck hunting in your tangents, you're going to get some nice lateral loads in your tangents, and then longitudinal loads. Well, the vertical loads come from the railway vehicles, the lateral loads come from the railway vehicles, the longitudinal loads come from the railway vehicles. Oops, wait a minute. We also have another actor in here. We have environmental effects, thermal loads. The longitudinal loads generated by in continuously welded rail by the simple expedient of the sun rising and setting or getting hot or cold are quite significant, of the order of 100 tons or more per rail. So all of a sudden you're seeing some really serious numbers there as well. Okay, so let's talk a little bit more. Let's start with the vertical load. The vertical load is the primary load used in engineering. If I'm going to start off a design of a new track, I start with the vertical load. I take a look at what my axle load is, my static axle load, my dynamic axle load, and what's happened. Well, if we look at the history, or let's go back here one more. If we look at the history of railroading, well, one of the things that differentiates us from our 19th century brethren is they had maybe 8,000-pound wheel loads, and we have 36,000-pound wheel loads. So we've gone off by a factor of 4.5. So all of a sudden, and that's just static. That's just the weight of the car standing still. In fact, the pace of the growth of axle loads, and as I'll show you in a moment, axle loads are growing, have grown, and will continue to grow, is set by the ability of the track structure to support it. Which means that basically no sooner do the engineers breathe a sigh of relief and say, hey, I figured out how to survive under 36-ton axle loads, the operating people and the business people say, great, let's go up to 39-ton axle loads because that's when I get some more economies of savings. And then we have high-speed rail loads, which introduces some really interesting dynamics, and that also introduces other variables such as the unsprung mass of the vehicle. In fact, when Amtrak introduced its Acela train, I was part of the team that was brought in with a very simple question. And the question was, we want to make sure that the dynamic loads going into the track, remember Amtrak has had a history of concrete tie fracture, we wanted to make sure that the dynamic loads going into the track when we operate at 150 miles an hour are no more severe than our old operations at 110 miles an hour. Well, that's engineering, people. And then we have to deal with issues like vehicle design, vehicle track dynamics, the load distribution and attenuation. But that was a real problem that they really had to deal with because they really didn't want to rebuild the entire Northeast Corridor because they introduced the higher speed operation. Okay, if we look at the static wheel loads in the railroad world, they're all over the map. Let's start from light to heavy. So in the transit world, we have light rail transit, the old trolleys now called LRTs, and they run about 8 metric ton axle loads, 9 short tons. You know, a metric ton is 10% more than a short ton, 2,200 pounds versus 2,000 pounds. So you look at a wheel load, so it's about an 8,800 pound wheel load. Heavy rail transit, again CTA for example, they're probably in the 13,000 pound wheel load, 13-ton axle load. Okay? Then we move up into the passenger equipment, and there we see numbers going up as much as 19-ton axle loads, except the fact that if you look at Amtrak, and you take Amtrak from Chicago to, let's say, Seattle, you're going to see a locomotive in the front end. And I promise you that locomotive is not a 19-ton axle load. That locomotive is designed to heavy axle load freight standards, which we'll talk about in a few seconds here. Okay, then we have our European freight limits. The UIC standard limit, the maximum allowable limit for axle loads in standard use in the Union of UIC is 22.5 metric tons, which is 25 short tons, or 25,000 pound wheel loads. The UK, in some selected properties, allow up to go to 25-ton axle loads, or 25 metric tons, 27.5 short-ton axle loads. Sweden, in a radical move that I have to admit I had a hand in, actually increased axle loading in Europe to about 30 metric tons. Why? Well, there was a mine, and there was an iron ore mine in northern Sweden that went from Kiruna, it was north of the Arctic Circle, froze my tail off every time I went up there, going to the port of Narvik in Norway, and they were competing with the Canadians and the Australians and the Brazilians, everyone who did axle loads. The problem was they were operating at UIC loads, and their cost of transportation was about 15 to 20% higher than their competitors. And so they were losing out in the world market. So they got together with the Swedish railways and said, we can't tolerate that. We need a heavy axle load. So the first thing they did is they did an economic analysis study, and we said, hey, they were right. And they went up to 30-ton axle loads, 30 metric ton axle loads, 33 short-ton axle loads. Okay, North American free interchange right now, today, we're at 36-ton axle load free interchange. Free interchange means a freight car can move anywhere from Canada, Mexico, and the United States without, as long as it complies with AAR interchange standards, without offloading it. I'm not talking about legal barriers such as customs. I'm talking about technical barriers such as imposed by the railroads. Then we have 39-ton axle loads, which, by the way, some of the double stacks, if they're not really careful on how they load, we can see 39-ton axle loads even on double stack operations. There are a few limited places in the U.S. Australia, a lot of the Australian mining loads are doing that, but the Australian mining loads have already since graduated. Fortescue Mining Railroad in Australia currently operates unit train operations at 41 metric ton axle loads today. And they run it on a conventional track. The same track you go out in the UP or the BNSF or anywhere else, you're going to see it. Same size rail, same steel, mostly premium, but the same steel you're going to find in the railroad, same concrete ties, the same basic infrastructure. And there's already talk that maybe they want to go a little bit higher. So we don't quite know what the limit is. If we look at the history of static, I'm still in the static world, I haven't even gotten dynamic yet. If we look at the history of static axle loads, you'll see that we've been on an upward trend. And in fact, it's been step functions. I personally lived through 2 of these step functions. When I came into the industry in the mid-'70s, they had just transferred from basically 220,000-pound cars to 263,000-pound cars. So they basically went from 27.5-ton axle loads to 33-ton axle loads. And the railroads were struggling, and the track engineering department was struggling. How do I maintain my track under these axle loads? And it took them a number of years. And by the time the 1990s rolled around, they had it all under control. So at that point in time, I was part of this one. The Burlington Northern decided, they had a very aggressive research group, and they decided they wanted to look at whether they were optimized at 33-ton axle loads. And we did a bunch of engineering economic studies and said, well, wait a minute, there's a lot of room for improvement. You can increase your bottom line. You can reduce your overall cost of operations by going to 36-ton axle loads because that reduces fuel, it reduces number of crews. You carry more paying commodity in a car. The ratio of what the shipper pays you to transport versus what you have to pay the dead weight of the car increases. And so they went ahead and they did that, and the rest of the industry said, hey, that's a good idea, and they followed. And now that's the 36-ton axle load that we're at right now. And that took about 20 years. So if we look at that cycle and say it took about 20 years, that was about the mid-1990s, hey, maybe we're about due to go to 315,000-pound cars. And by the way, they've been studying 350,000-pound cars from an engineering aspect in Pueblo with the Facility for Accelerated Surface Testing since the 80s. So it's not as if we're not looking forward to it. We know it. We have a lot of engineering data. And as I sit here with my crystal ball of the future, I will tell you, I don't know if it's going to be 5 years or 10 years, but I will tell you that at some point in the not distant future, the railroad industry will move up. Because as I said, the Australians are already are well past that. They're up to 43,000-pound wheel loads. So for us to go to 39,000-pound wheel loads, we're not even going to be in the Australian world yet. And this is what a nice, for you, every once in a while you got to throw in a nice picture because railroads have pretty pictures. And so this is a nice, long, heavy freight train, probably about a 14,000-ton freight train going through the Canadian Rockies. Okay, so far we've been standing still. So let's start moving. Okay, so if we look at the speed regimes of different operations, transits, because transits really have to go short distances, there's no point in accelerating to 90 miles an hour to slam on the brakes to go to stop at the next station. You can get the same benefit without the energy waste by just simply going at 50 miles an hour. So you very seldom see transit more than 50 miles an hour. Heavy axle load freight, excluding double stacks and intermodal, which come down here, 40, 45, 50, sometimes maybe 55. But again, you know, coal is not on a rigorous schedule. It's more a question of reliability of shipment as opposed to how quickly you can get it there. Coal is certainly not going to perish. Iron ore is not going to perish. Even wheat, it's not going to you're not going to have a problem if it takes an extra day to get to shipping to the ship. So we can tolerate that. Conventional freight maybe goes up to 60. Intermodal, okay, well, if it's Christmas season and Walmart shipping the containers, the Chinese containers to the East Coast, well, they want to move a little bit faster because they do have a schedule to meet. So double stack trains can operate at 79 miles an hour, rounding it up to 80. The FRA actually won't let them do 80 unless, for a variety of reasons, unless the signal system is, but they can go to 79 miles an hour very nicely. And then interurban passenger and commuter, they can go up to about 90. Then we have that American term, I haven't seen this anywhere else in the world other than the FRA, called higher speed rail. And higher speed rail sort of fills the vacuum between 90 and 125 miles an hour. Then we have American high-speed rail, which is about 125 to 150 miles an hour. And then we have the rest of the world's high-speed rail, which is 180 plus. The Chinese are over 200. I've ridden trains in China that have gone over 200 miles an hour. So, and we're still looking to improve that. And of course, just, you know, remind everybody we got pictures of trains. Okay. So now, once we start going at speed, our static loads become dynamic. And in fact, when we're doing our engineering analysis, we're going to deal with dynamic loads. So dynamic augments to static loads are significant. They're due to track geometry imperfections, which the higher you go, the greater the effect, which is why track geometry standards get tighter and tighter the higher your speed you go, specifically because of the dynamic loading and the dynamic behavior. Rail and wheel surface defects and wheel defects, I promise you, are significant and dramatic, and they have to be controlled, which we are doing. Increases in operating speed and unsprung mass, stiffness transitions, and all sorts of things which we can spend an entire semester talking about, much less an hour lecture. So dynamic impact factors of 4 or greater of the measurement field. So I have my 36,000-pound AAR interchange load. We've measured loads over 140,000 pounds per wheel dynamically. And there's lots of data out there that shows that. And that does all sorts of nasty things to rail and ties and ballast. So much so that the AAR interchange limits have finally put in a dynamic load. In the past, the idea was, well, we don't want to have wheel flats, and we don't want to have certain other classes of wheel defects that we know generate dynamic loads. But the problem is there's always something else that comes in. We have outer round wheels. My favorite, we have the eccentric, the off-center wheel, where the axle doesn't quite go through the exact center of the wheel, offset maybe by a couple of millimeters. Effectively, an eccentric rotation generates dynamic impact loads. So what the industry does, which is rather clever, is we measure. And we have wheel impact load detectors, and we put a limit of 90,000 pounds. Remember, we're still talking about a 36,000-pound static wheel load. So we're still allowing almost a factor of 3 increase in dynamic loads. But we have limited it. And in fact, if we measure 120, we stop the train, period. 90, we sort of let it hobble to the nearest shop and replace it. And then we've done something very, very clever that sets us apart from the Europeans. Because we have the interchange system in the US, if the Burlington Northern finds a 95,000-pound wheel from a car that came from a power plant in Georgia, let's say, they can take their car to the shop, change out the axles, and send the bill to the owner of the car, and he has to pay. By the way, our European friends are green with envy over that. Because the Europeans also, I've spent some time overseas talking about this issue, and they also look at about a three-type dynamic impact factor. And they can measure it just as we can, and they can take the cars out just as we can, but they can't send the bill to the owner. So every once in a while, there's some interesting ramifications that come through here. Okay. If we actually look at field measurements of dynamic loads, which is a good way to get a distribution, we see that between 0.1% and 0.5% of all freight cars experience dynamic load, freight car wheels experience dynamic loads over 75,000 pounds, which is more than double static. Well, 0.1%. If I have a 120 car freight train, one freight train, that's 1,000 wheels. That means I got one wheel in each freight train that's over 75,000 pounds. So, and that's allowable. That's well below the 90,000-pound limit, but it's doing a lot of damage to my track. And again, part of where we're going and what we're doing and how do we be engineers in this world. Okay, that's just the vertical load. Now we have the lateral load environment. Lateral loads environment is associated with the way we go around curves. Again, the use of the rolling radius differential in the wheel sets only goes so far, and then we generate loads. We have centrifugal effects, we have curving forces, and they generate loads that be quite significant. In fact, so much so that high-speed railroads really don't allow curvatures greater than 2 degrees, and some of them won't even allow curvatures greater than 1 degree. You go to a high-speed railroad, a 1-degree curve, a 5,000-foot radius curve, is a sharp curve. Now go over to the Union Pacific and tell them that a 1-degree curve is a sharp curve, and they'll laugh. But go to the TGV in France and tell them, and they'll say, oh yeah, that's a sharp curve. Okay, so we have centrifugal force, we have curving force. Most freight trucks or freight axle sets do not remain radial to the curve, so we have this nice angle of attack, and so this wheel set sort of goes bouncing around the curve, generating nice dynamic loads. Okay. So lateral loads include steady-state curving, such as our centrifugal forces, transient forces, such as our curving forces, again, localized slip-related forces, flanging forces, which are related to the curving forces. And all in all, we see lateral loads that can be as high as 30,000 pounds, in addition to vertical loads. And what does that mean? That means that we can see some of the very high-stress conditions that are normally associated with heavy axle loads in curves just because of the higher lateral loads. And I'll give you a specific case of that in a few moments. Loads in the 15,000 pound range are quite common, and when we get to L over V ratios, that's a ratio of lateral to vertical loads. If you're in Europe, we call them Y over Q. I have no idea where the Y and Q terminology came from, but they call lateral loads Y and vertical loads Q. But an L over V ratio greater than 0.8 starts our potential for wheel climb. Varies with a lot of factors, but that's sort of a rule of thumb type of starting point. And then we have longitudinal loads, as if vertical and lateral is not enough. So start off with our mechanical loads. Well, what do we have mechanical loads from? Well, first of all, I got trains braking into stations and accelerating into stations. Okay, what kind of forces they can give me? Well, New York City built a people mover going into JFK called the Air Train. And if it's a 5-ton axle load, I'll be shocked if it's that heavy. Okay. But there's a fairly steep grade. There's about a 10% grade on that route. And after about 6 months of operation, I got a call from the engineering people saying, our rail is moving longitudinally under this 5-ton axle load 2-car train set one that's running every 2 minutes. Why? Because I'm braking going down that grade. and I'm generating longitudinal forces. I'm braking going into that station. I'm accelerating coming out that station. I'm braking going down the mountain. I go over the Rockies, I'm braking. I'm generating longitudinal forces. I've measured, we have measured, or the industry has measured longitudinal forces as high as 60,000 pounds per rail. Again, significant forces. And while that's high, 20, 30,000 forces are more realistic. Well, that's the mechanical forces. Wait a minute, there's another issue. I have continuously welded rail. Well, rail should be able to expand and contract when it gets hot or cold. Well, not if it's anchored. Not if it has fasteners holding it down. It can't move anywhere. So if it wants to expand, it gets locked up. It generates longitudinal forces, compressive. If it wants to contract, because it gets cold outside, this is the Midwest. You guys get cold out here. You get what? 5 below, 10 below sometimes? Okay. So rail wants to contract. It can't. That's tensile forces. 100-degree Fahrenheit temperature change. And by the way, you go to some places say on the Burlington Northern or the Alaska Railroad or Trans-Siberian Railroad, where the temperatures go from -40 to +120, and then tack on another 30 to 40 degrees of rail temperature, because the rail is a black box sitting in the sun, and the rail is 30 to 40 degrees higher than the ambient temperature, and you suddenly can see temperature fluctuations. 100-degree temperature fluctuation is not at all that unusual in those situations. 100-degree temperature fluctuation will generate 250,000 pounds worth of longitudinal force per rail. I was involved in a light rail system. They were building a really fancy bridge in it. And it was a place where most of the bridge designers were highway bridges. So what do they do? How do you design a bridge? Dead load, drive load, wind load. Okay, well, hey, guys, what about rail load? What's rail load? Well, if I have 2 tracks going through my bridge, which is only having a transit bridge, I have 4 rails, at 250,000 pounds per rail, that's 1 million pounds of longitudinal force. Does that affect my bridge design? You bet it does. So again, if you don't know your loads, you can't even start doing your engineering design. Okay. High-speed rail. As we indicated, high speed has a really major effect on the dynamic loads. And as I indicated, there are all sorts of definitions. So you can either call European high-speed rail or the rest of the world high-speed rail is sort of in the 180, 200, 210 mile per hour world. The American high-speed rail is sort of the 150, 125 to 50 miles. In fact, FRA defines high-speed rail as 125 to 50 and defines higher speed rail, as I said before, between 90. And you can see we got, Class 8's 125 to 150, Class 7's 110 to 125, Class 6 is 90 to 110, etc. Okay, so we have a whole bunch of issues associated with high-speed rail, and then we have a whole bunch of issues associated with mixing high-speed rail with heavy axle rail, which most of the world doesn't, but crazy Americans do, certainly in the Northeast Corridor. So again, we talked about maximum allowable curvature. We want as small a curvature as possible. We want to design to a minimum curvature. So curves less than 2 degrees at worst, and probably less than 1 degree. By the way, it's only the Americans who talk about degrees. The rest of the world talks about meters of radius. So again, you got to be conversant in both. You need to be able to translate degree to curvature and your radius in your sleep. That's a good exercise for students. Okay, elevation, because I'm going around even these sharp curves. Very tight geometry requirements. As I said, imperfections in the track structure. Oh boy, I'm still talking. I'm on a roll. I'm not even halfway through my presentation. What time can I go till?
5:30 is when it cuts off.
Okay, we'll try to speed it up a little. A couple of things I want to show, so we'll go through it. High-speed track geometry requirements, enhanced grade crossing protection, etc. And then we have the track maintenance issue. Because, okay, so one of the issues we have, seriously, one of the issues we have is high-speed rail has very, very tight geometry standards because of the dynamic load environment. If I try to run heavy axle loads on that, well, heavy axle loads will tend to increase my rate of geometry degradation. So all of a sudden, I'm playing catch-up. I run heavy axle loads on a high-speed railroad. My geometry degrades. I could either be constantly doing maintenance, or I got to slow my trains down, or I got to get rid of my heavy axle loads, or I got to improve my design and my maintenance planning and my forecasting. You can see there's an interesting cycle and interchange in here that you have to deal with. Okay. Curvature and speed, just to show you real quickly, your 120 mile an hour, your 180 mile an hour railroad has to drop to about 120 miles an hour in a 1-degree curve, 85 miles an hour in a 2-degree curve, and if you let a 5-degree curve creep in there, you're down at 50 miles an hour. So all of a sudden, and you have to accelerate, and you have to brake into the curve and accelerate in the curve. So it's not, I just stop right and I go from 180 to 50 and go back up to 180. I mean, I gotta brake, and at 1 mile per hour per second or less, that takes time, distance, energy, etc. Okay. So as I talked about, railroad engineering can be broken into design and maintenance. Design-based engineering, load-dependent, sort of the grandfather of engineering design is the beam and elastic foundation model. Beam elastic foundation model basically says that the rail acts as a uniform beam supported by a series of linear springs. That's the basic model given by this nice, easy, straightforward fourth-order differential equation. No dynamic component, otherwise this would translate into a partial differential equation in both distance and time. No shear component, that would add a W double prime, a second-order effect in here. Oops, went too fast. And then we put a concentrated wheel load over here, and hopefully many of you have seen the results, which is the deflection and moment curves which we use to generate the behavior of our track structure. There are a lot more sophisticated models out there, both closed form and finite element, but over the years, or over the decades, because the beam elastic foundation actually also dates back to the 19th century, developed by a fellow by the name of Winkler in Europe. It's such a good model, relatively easy to use, relatively accurate, that, using it today probably still works pretty well. And I will attest to that, because I still use it to this day. And even though I have other models, much more sophisticated models available to me, this functions quite well in predicting my behavior. It also tells me that I'm going to get liftoff. So if I have a wheel here, my track is going to lift off over here, and you go out in your railroad and you watch a wheel go by, and lo and behold, the rail does lift off. It actually does duplicate reality. Okay. Maintenance-based engineering, as I said, is concerned with the long-term performance. Different focus for heavy axle load and freight and high-speed rail. For example, in the high-speed rail world, geometry is everything. Rail lasts a long time, ties last a long time, focus is on geometry when I'm doing maintenance of my track. In the heavy axle load world, rail is the big dollar one, followed by ties, followed by geometry and ballast. That's number 3. Still significant, but nowhere near as large as rail. So all of a sudden my focuses have changed. Why? Because my degradation mechanisms and my degradation modes have changed. And so maintenance has been a focus, and it continues to be a focus for both heavy axle load and high speed, and every once in a while they converge. And ultimately, safety creeps in, because when we're doing maintenance, we have to, when you talk about standards, there are 3 sets of standards. There are construction standards, which is I build my track to very tight. There are maintenance standards, which is I maintain my track to, which is a lot looser than construction. And there are safety standards, which I am not allowed to go beyond without slowing my train down, because that results in a potentially unsafe situation. So setting my standards, looking at how much time it takes me to go from maintenance standards to safety standards, that's all part of the maintenance engineering and modeling. Okay, so continuing on to the world. So let's talk a little bit about rail. And I want to at least I want to get to a couple of rail issues here, because they're interesting issues. If you look at that wheel-rail contact zone, and you look at the behavior of the rail, you see the rail suddenly sees a whole bunch of interesting simultaneous and concurrent loading. Just looking vertical, let's take the tangent track. So let's not even talk yet about lateral loads, and let's not even talk about longitudinal loads. Let's just talk about vertical loads. Okay, so first we have that wheel-rail contact stress, that 100,000 psi, which is very local to the surface of the rail, degrades very rapidly. So that by the time I'm halfway through the head of the rail, my contact stress is negligible. Then I have my bending stresses. My bending stresses are 0 around the neutral axis and maximum in my head and my base. And depending on where my load is, I'm either in tension in the base and compression in the head or vice versa. Then you can see that, so I go from negative to positive and then reverse when I have my uplift. Then I have my thermal stresses, which are nice and uniform through my rail section. By the way, there's another stress in here, which is my residual stress, which is locked in during the manufacturing process. All of these act concurrently. So what they do is they compete with what ways does the rail fail. Is it going to fatigue? Is it going to wear? Is it going to pull apart? Or what are my mechanisms? What mechanisms do I see in the railroad world? All of the above. And part of my issues is how do I address the different mechanisms. Okay, so wheel-rail contact stresses. Wheel-rail contact stresses is this 36,000-pound wheel load, which is allowed to go up to 89,000 pounds dynamically, hitting the rail in about a contact area of about yay big, maybe about 1/4 of a square inch. So I'm in plastic. I've already gone plastic. I'm already beyond the yield strength of my steel. So right away, I've got to deal with that. If I look at it on a photoelastic basis, this is a photoelastic model of good wheel-rail contact, because I'm nice and centered. My wheel is sitting very cleanly on top of my rail. You can see, and by the way, it's the number of rings that count, you can see there's a significant number of stress. Now let's introduce lateral loading. And my lateral loading can be introduced by way of 2-point contact, which means I have one contact point between the flange of my wheel and the tread of my rail, and the flange of my wheel and the gauge face of my rail, and the tread of my wheel and the head of the rail. Or I can have 1-point contact, which is what we see when the rail wears in. So you go out to a curve on the UP or the BN or the CS or NS or FAST or anywhere else, you'll see this very high conformal wear, and you'll see this 1-point contact. And what happens to my stresses? Well, if I remember I told you the number of rings here relates to the number of stresses. Well, I've got a lot more rings in this picture than I have in the previous picture. So again, I get to the point where I don't even need a heavy axle load environment to get me into yield, because I have a combination of vertical and lateral loads on that same point, then I can actually go into yield stress and generate fatigue as well. So contact stresses are the first actor. Contact stresses are very interesting. If we look at the normal contact stresses, as you expect, they're the maximum on the surface. If we look at the shear stress, something very interesting happens. The maximum is not on the surface. The maximum is about 8 to 12 millimeters below the surface. By the way, when we look at most rail failure mechanisms, such as shells in the rail, where do they initiate? They don't initiate at the surface. They happen to initiate about 8 to 12 millimeters below the surface at the point of maximum Hertzian shear stress. Pure coincidence, of course. So, wear versus fatigue, what dominates? Well, it's a function of axle load. It's a function of curvature. Under light axle load, so our European friends, they primarily get, they'll get wear and some fatigue. Here in the heavy axle load world, we get a tangent track. Tangent track almost never wears out because fatigue comes much too quickly. Curves, where I have my high lateral loads, there I can start to have competition between wear and fatigue. If it's dry and unlubricated and standard steel, it's going to wear out. If I lubricate it and put premium steel in there, so I stop the wear or extend the wear life, then fatigue starts creeping its ugly head in, and then I have to deal with fatigue. So again, Wear includes head wear, gauge face wear angle, all measures that we use. We have all sorts of nice technology ranging from the stuff they used to use when I went into the industry in the way back, you know, sort of the old carpenter's gauge, to laser-based vehicle-mounted rail profile measurement systems, which are the norm. Every major U.S. railroad has at least one of these. Every one of their geometry cars has one of these running down the track, taking nice profiles of the rail, measuring the wear, measuring the profile of the rail. It's state-of-the-art technology. How do we use that data? That we're still trying to figure out. Because as the technology is moving forward and we're getting more and more high-tech toys to measure our stuff, we're also drowning in data and we're trying to figure out how to deal with the data, which is a topic for another presentation or a complete conference, which I run in Delaware. So if I look at, so that was wear. Okay. Then if I start looking at the surface, I suddenly start seeing this fatigue behavior. I see surface cracking, what we call rolling contact fatigue. I see the subsurfing cracking at the point of maximum Hertzian stress, and that's going concurrent, so I'm wearing. So if I have a very high rate of wear, this is not a problem, because I wear so quickly, I get rid of the stuff before it develops. So I can solve my fatigue problem by allowing my rail to just wear very rapidly. The problem is that means I'll be replacing all my rail for wear every few years, which is not a good engineering solution. So I lubricate it, and I stop my wear, and all of a sudden I allow my fatigues to develop, which is one of the trade-off issues that we deal with. So this is a fairly common type of rolling contact fatigue, a little bit advanced. By the way, you notice it's not quite normal, it's at an angle. That's because there's a longitudinal slip component, a lateral slip component. In fact, just the dynamics of the contact stress has been given birth to many conferences just dealing with the behavior at that local, the tribology at the wheel-rail interface. That results in the development of subsurface shells. Subsurface shells turn around. Here you can see the development of a subsurface shell. Grows longitudinally, not nice. But what's even worse is when they grow transverse. And this is a detailed fracture generating from a shell. This is the single largest source of derailments and failures in the United States. We, in the United States, take out about 200,000 rail defects a year. That's the U.S. alone. That's about 20% of the world. We're a little bit ahead on a rate in the world because of our axle loads. But we take out 200,000. We have less than 200 derailments, which is not good, but those broken rail derailments. But that means we find 99.99% of all the stuff without a problem. It's the 0.01% stuff that's a problem. We'll talk about that a little bit. Okay, and this is one of the problems. I like this slide. This is a detail. You can see this is a fairly large defect. If you look closely, that defect never broke the skin of the rail, which means that if I have my track inspector walking down the track, he's going to see a perfectly good rail. I need ultrasonic testing, or maybe somebody will come up with a even better technique, but ultrasonic testing is about 90%, not plus of 90% effective, so it's a good starting point. But I need technology to find this type of defect. Which takes me to a derailment, which I use as an example. This is the Hatfield derailment that occurred in October 2000 in the UK. I happen to be very familiar with it because I was part of the team that was brought in by Network Rail at the time, actually it was Rail Track, to make sure it never happened again. Very interesting. First of all, it was a rolling contact fatigue defect, which is a North American heavy axle load defect, which the British said did not exist in the UK. I remember having specific conversations with colleagues in the UK saying, you guys have these high axle load stresses, we don't get those kinds of fatigue defects. Okay. At the time they were inspecting for defects, they were using a probe, a 0-degree probe. They were just going straight down the center of the railhead. Well, detailed fractures or rolling contact fatigues are over in the gauge corner. If I'm looking at the center of the rail, I don't see it. So they weren't even looking at the gauge corner. Okay. So in October 2000, a high-speed intercity train running at about 115 miles an hour derailed, killed 4 people, injured 70. By the way, it only killed 4 people because there was a whole discussion about the crashworthiness of this particular car. A German accident that happened a year later at the same speed killed 109 people because those cars were not crashworthy. So they were lucky that only 4 people were killed. Okay, so this was a rolling contact fatigue defect, one they never saw. They weren't even inspecting for it. So the first thing they did is, maybe we should look at the gauge corner on the rest of my railroad to make sure there are not any more of these. Well, they went out and they tested their railroad, and they found hundreds of them. So much so that it took them months to get all those defects out. Meanwhile, they had to slow order the trains. At that time, the infrastructure company, Railtrack, was a separate entity than the operating company, so they had contracts with penalty clauses, which basically told the operating trains that if we slowed your trains down, you pay us a penalty. Okay? The penalties associated with the post-Hatfield defect fines came to 7 billion pounds. Now, in those days, a pound was about $1.50. So that was about $10 billion. It actually bankrupted Railtrack, which was a private company. They actually declared bankruptcy, and the government had to step in and form a quasi-governmental type of corporation called Network Rail, which exists to this day, to take over. But the penalties, just from the fact that all of a sudden they went out and looked for these defects, which are a combination of vertical lateral loads on the gauge corner of the rail, came to about $10 billion and bankrupted the infrastructure company. The obligatory derailment pictures, of course, never a pretty sight. When people are killed, cars are on their side and crushed and things like that. Okay, so the rail fractured over the train, a very, very common occurrence. Why? Because there are high dynamic loads. Remember, we allow 89,000-pound wheel loads. One wheel a train is probably 75,000 pounds on average. So we have these high dynamic loads. And so if I have a defect that maybe represents 30 or 40 or 50% of the head area of my track, and along comes a wheel, it's probably the 45th wheel or the 350th wheel in the train, with that said 80,000 pounds, it breaks it. Which explains, by the way, why the 40th car of the train derailed when 39 cars ahead of it did not derail over that same defect, which is always the question that gets asked. So this was gauge corner cracking due to rolling contact fatigue, developing a detailed fracture from shell, and as I said, when they actually went out and did a real inspection at the right location, they found hundreds of them. Now, coming back to the U.S., actually, I think the last couple of years were a little bit less. I think we may be down to about 170, 180 rail-caused derailments. But we get about 200 rail-caused derailments a year. Average derailment cost is about $228,000. Expensive derailments. These are FR-rated costs, by the way, which only includes track and equipment costs. It doesn't include cost of train delay, cost of rerouting, cost of the lading, etc. That's not included in any of these costs. True cost is probably more than $400,000. Why so expensive? Because these derailments happen at speed. Because these derailments are on a main line, because that's where you get the high dynamic loads if you're going to break under a train, and so you're going to get so you have all that energy. We basically have about roughly 1 derailment for every 1,000 defects we find, which goes back to we find 200,000 defects, and we have a little bit under 200 derailments a year. Okay, thermal load related problems. So jumping now from rail, let's talk a little bit about thermal load related problems. Now remember, we talked about the fact that longitudinal force is a function of temperature. I mean, you can see here, we're looking at 200 to 250,000 pounds per rail. We generate some very big forces. Okay, so if it gets cold, we're in tension. What happens? We have a pull apart. Pull apart means we either rupture the rail, sometimes there's a weakness, sometimes there's a weld. So very often pull aparts are joints where we shear off a couple of bolts. But again, depending on the change in temperature from the neutral temperature, rail is locked in at a certain temperature. And so if we have if we lock the rail in at a very high temperature and it gets very cold, I have high tensile stress, I have a pull apart. So obviously we should lock the rail in a very low temperature. Well, then if it gets hot, I get a buckle. And if I go to my track people or my operating people and I say, which would you rather have, a pull apart or a buckle? What are they going to say? I'd rather have a pull apart. Why? Because my signal system will tell me I have a pull apart and will stop my train. If I have a buckle in front of my train or under my train, I have no warning until the engineer sees it. He's going to probably slam on the brakes when he sees it. What's going to happen when he slams on the brakes? He's going to put a nice longitudinal compressive force into that rail. What do you think is going to happen to that buckle? It's going to expand, right? So the normal reaction of the engineer is going to be actually the absolutely worst thing he can possibly do. And again, there's a whole history of derailments associated with just that happening. He sees the buckle, puts the train into emergency, generates this nice additional longitudinal force, and so what may have been 6 or 8 inches suddenly becomes 14, 15, 20 inches. And looks like that. And no train's going to go across that, people. Now, if I had the time, I'd talk about the fact that the buckling phenomenon is very interesting. There's a whole body of work on this. It is not your classical Euler bifurcation buckling. It's not your classical column bucking. It's basically what we call a non-bifurcation buckling phenomena with a stable state, an unstable state, and a stable state, and that's where we get the snap-through buckling, which means that basically I'm straight 1 second. I didn't put any videos in here. I have a nice video, but I didn't take the time to put it in here. And this just literally snaps through. So it's not a gradual process, it's a snap-through process. And then it releases the longitudinal forces in that zone. This is a derailment of an Amtrak train on CSX a number of years ago. There's a very detailed NTSB report out on this that you can look at. Classical overview, you can see that. This was a case where there was maintenance work done that disturbed the ballast tie interface, that reduced the lateral resistance of the ballast and the shoulders, the ballast shoulders and the ties, and made this track susceptible to a buckle, which happened. And this was another case where the engineer dropped, slammed on the brakes and increased the size. Okay? If we look at the distribution of accidents by cause, and we look at the distribution of track accidents. First of all, okay, let's first of all look at all accidents. Traditionally, and if you look at FRA statistics, and by the way, this is all online. I'm sure you all know this is on the FRA website under their safety group. You can see that human factors and operations are the largest percentage by number, but there are a lot of low-speed yard derailments here. Track is consistently number 2, but there are a lot of expensive high-speed derailments here. Or not high-speed, track speed derailments. Equipment's less, signaling is even less, and then miscellaneous always has a bunch. If I look at my track ones, I see a large number of track geometry, rail and joint bar, frog and switches are sort of number 3, and then everybody else is sort of in the noise ratio. If I look at it, though, a slightly different way, if I look at it from the point of view of not just the number of derailments, but the cost of the derailments. So I take the number of derailments and I add up the cost of the derailments. So I look at the total cost of the derailments. This is a summary for about 10 years, 2005 to 2010. And it turns out that broken rail derailments are my most expensive overall category of derailments, followed by track geometry. I get more track geometry defects than I get broken rail derailments, but they're less expensive because a lot of them happen at lower speed. Followed by wheels and axles, which, by the way, on a per derailment basis are more expensive, but you can see there's maybe 15% of these. So, what just happened? Okay. So you can see, well, here I have a fewer, but I have very expensive ones. So if I look at his numbers, this would probably be number 10, 12, 15, and instead it's number 3 because it's such an expensive derailment. Okay, so if you look at the top 5 categories, they're either track or equipment, and they're mostly engineering related. Broken rail, broken wheels, wheel rail dynamic geometry, frog switches. I don't get to operating issues until numbers 6, 7, 8, and 10. Even though that's the greatest number, and again, you can see the numbers are pretty high, but they're less expensive. Okay, wrapping it up, since I'm only, I'll leave a few minutes for questions. Everybody's going to run out the door anyway when I stop. Future of railroad engineering. Future of railroad engineering is bright. Railroads are going to be around for a long time. Warren Buffett liked the railroad industry so much he bought the BNSF. So, you can see it's not just me talking. People who really look at the finances are talking about it. You look at any new city being built, or any growing city, you're going to see a new rapid transit system, either light rail or heavy rail. I like the story of Los Angeles. It's my favorite story. Los Angeles had a wonderful rail system in the early part of the 20th century. Along came the highway, the car era and the highway area, and they tore up their entire trolley system and rail system. And then, of course, we all know about traffic in California. So along come the 1970s, and they had to build their new red line from scratch. So they built the red line. That was such a success, they built 5 other lines since then. And they're still looking to expand. So they've gone from rail to cars, back to rail. And no modern city. And like I said, if you look at sustainable cities, everybody's going to talk about metros. So, and when you build them, somebody needs to do the engineering. As we said, some of these problems are not just, let's just increase the size of that rail. That doesn't work. We really need to do real engineering. So you guys have some jobs out there. That's the good news. It's going to evolve in the axle load. Like I said, I think axle loads are going to increase relatively soon. High-speed rail is coming. They're building California right now. We're going to get what we're going to get. Amtrak's ordering some new equipment that's going to go greater than 150 miles an hour. They're going to have to do something to their infrastructure sooner or later. Get rid of some of those curbs, upgrade their speeds. The track structures are going to continue to evolve both from a weak spot point of view, from a maintenance point of view, and from an engineering point of view. Incrementally for the most part. And I think that's the way it's going to till you go. There's a potential for development of new track systems, but I still think I'm still putting my money on incremental over the next 10 to 20 years. One of the big areas of growth in the track business, as I said, is inspection technology. We're developing tools to inspect underground. We now use ground penetrating radar to look at the condition of the subsurface, of the subballast and ballast conditions. We're looking at all sorts of nice, neat new technologies as generating tons of data. We're generating more data than we can store. I know railroads have told me that their geometry cars generate more data than they can physically store. And that's, and storage is involved and technology is involved. And so another interesting, exciting, and bright area of future is how do I use that data to make my railroads more efficient, more effective, more cost-effective, and by the way, even passenger railroads need to be cost-effective. Just look at Amtrak in the Northeast right now. They're struggling for money. They need to be more efficient as well. So it's not just the for-profit railroads, it's also the public railroads. And that's worldwide as well. The French government doesn't support the SNCF the way they used to. The Germans don't support the Deutsche Bahn the way they used to. Railroads have to become more efficient. And by using information and information technology, we have an additional tool to try to make things more effective. And with that, I thank you. We have time for a few questions?
Time for a few, yeah.
Thank you for the I mean, when you are combining the high-speed rail with the freight rail?
Okay. Well, first of all, as I said, that most places in the world don't combine them. And the reason is heavy axle loads increase my rate of degradation. High speeds gives me very, very little tolerance for degradation. So if I have, I'll talk about Amtrak and Northeast Corridor because they deal with this, and it's a practical issue. Amtrak's operating at class, FRA class 8. And so they have, let's say they have allowed a half inch of surface degradation. Okay? Under normal passenger operations, maybe that it would take a year to 2 years to degrade. If I start running heavy axle loads on that location, I may be degrading in 6 months. I may be degrading in 4 months. So all of a sudden, my maintenance window for my entire railroad has been compressed by a factor of 2 and 2.5. Okay? I'm introducing a more rapid mode of rail failure. We talked about buckling. Buckling has a component that's associated, because there are a lot of buckles that happen under trains. Now, not just in front of the trains. Why under the train? Because we have an uplift. Remember the uplift wave and a beam and elastic foundation? So what happens? I have an uplift in front of my wheel. I pick my tie up. All of a sudden, I have 3 elements of friction that are resisting my movement of my tie for buckling. I have the end. I have the side. The side of my tie is against my ballast cribs. And I have the bottom of my tie against the top of the ballast. That represents about 20 to 25% of my total lateral resistance based on testing. What happens if I just lift it up? I've just lost 25% of my lateral resistance. And if I have a heavy axle load, that's going to lift it up a little bit higher, so I'm going to reduce my crib size as well. So all of a sudden, I do have a crossover. I do have a trade-off in effect. And we see that type of trade-off in most failure modes. Oh, I'm sorry, I was supposed to have repeated that. Why don't you do the mic here?
Well, I just saw today, actually, that Siemens just announced that they're going to be doing a lot of data storing and analysis for transit or rail companies, and I'm curious, in your experience, is that typical for railroads to go to outside companies to do that, and what data are they most interested in?
In the United States, it has not been the trend. Okay? I mentioned that I run a big data conference at the University of Delaware every year, and I've been fortunate to have representatives of your program give presentations in the last couple of years. So it's we have railroads, we have suppliers. IBM made a very interesting presentation. IBM is currently working with the SNCF right now, doing some of that for them. Will the railroads go to outside sources, or will they create their own internal departments to do that? Railroads have, certainly American railroads have traditionally liked to bring the expertise in-house. What I see, and I see this even in my conference, because I see people coming from railroads who are part of a new group, which is a data analysis group. Non-traditional railroaders, not guys who come up, having been a roadmaster or having been a division engineer, but guys who are hired with a PhD in mathematics or in industrial engineering, looking at how do I analyze my data. So I'm seeing both. I'm seeing some railroads turning to outside agencies, and by the way, there's a big push by a lot of the companies because they see this as a potential market. But I'm also seeing railroads building up that expertise in-house. And I suspect, like often happens in our industry, you're going to have some railroads doing A and some railroads doing B. And if I had a bet, I said, I'm going to bet that's what's going to happen.
Any other questions? I think you answered all of the questions.
I got one more.
Oh, okay. Good.
Separate topic.
Okay.
I'm kind of interested to see how the Brightline train in Florida does, and the new well, the high-speed rail that they're trying to put in Texas just because they're private endeavors. And I'm curious, do you think that any passenger-type service will return to freight railroads? Would they be interested in making money off of that in the future?
I think first of all, that's two different questions. The questions are, will passenger service return to freight railroads, and B, are the freight railroads interested? As you know, Amtrak, the freight railroads weren't given any choice about Amtrak. That was federal legislation. And I suspect that a lot, there's been a lot of discussion recently, and there have been a lot of cooperative work. Again, let's take Chicago, Metra. Metra owns virtually no track. Metro operates on BNSF, CP, the old IC, UP. They operate on railroads. And they're, in fact, by the way, cost allocation is a very interesting engineering application as well. Because if I'm running heavy axle load freight and a high-speed passenger, an intermediate passenger, and how do I distribute my maintenance costs? Does a ton-mile at 125 miles an hour equal a ton-mile at a 36-ton axle load? There are legal cases, there are STB cases, there's a whole engineering subset associated with that. And that's an issue that they have to address if they're going to run passenger trains on freight railroads. That becomes a really practical issue, because that becomes, what does the freight railroad have to pay the passenger? When Amtrak started running on the freight railroads, there was a whole series of litigation at that time before the old Interstate Commerce Commission, just dealing with that to resolve that issue. So, first of all, I see, there's some lines where the freight railroads say, you know what, I can get some extra revenue out of this. Maybe it's a good idea. There are some lines that they're saying, wait a minute, I'm bursting to capacity with freight. I don't have time to give up my capacity for passenger. And we're seeing a lot of that. The commuter operations, a lot more and more of the commuter operations, they're either running on freight railroad track, or they're actually buying the track from the freight railroad, which is another option. So, do I see, if I had a crystal ball, my magic crystal ball, do I see an increase in passenger operations? I'm seeing it. I'm seeing it. Is there going to be competition between who's going to use the track? Yes. Are they going to have to reach some accommodations? Of course they will, but it's going to be, this is going to be an economic decision as well. If they if they can reach an effective economic decision, they won't need government intervention. If they can't, then maybe they'll need a government intervention. How that plays out is still a big question mark.
It depends, is what Professor Zarembski would always tell us in our classes. It depends. That was his catchphrase.
Okay, I think everybody wants to go home.
What is your opinion about
Can you
balance track?
can you just repeat it into the mic? They've told me that I've got to...
What is your opinion about the future of ballastless track in the U.S.?
It's alive and well and staying. It has its role. It's cheaper, and nobody's going out and replacing 200,000 miles of ballasted track with slab track anytime in the next 50 years. Are we going to see, as we build high-speed lines, are we going to see more non-conventional tracks, slab track, direct fixation track? Sure, we will. But nobody's going to go out and plow out the, and the reality is, for the freight railroads, remember my opening statement, the World Bank says the North American freight railroad system, the U.S. freight railroad system specifically, is the best in the world. So you're not going to argue with success. It's economical. When you do life cycle economics, when you do any of the economics using U.S. type costs, like U.S. costs for wood versus concrete, conventional ballasted track still seems to come out very, very nicely ahead. That's not to say that maybe we're going to see an increase in spot utilization, but I don't see any massive changeover. No.
Thank you for your presentation. I really enjoyed it. Actually, during your presentation, you mentioned quite a few trade-offs. And I'm actually interested in, because that will affect your decision-making. So how do you usually identify and evaluate or quantify your trade-offs? Do you usually apply your heuristics where you have specific guidelines to aid your decision-making?
That's an excellent question. It depends what your trade-off analysis is. If you're dealing with a lot of the classical engineering trade-offs, such as maintenance-related costs, for example, if I was doing analysis of wood versus concrete ties, and by the way, I have done those analyses a number of times, most of those trade-offs are easy to quantify because I can quantify